Uh, if you're looking for challenges, Liam, uh, so this does use the same genetic algorithm, and these towers don't slow down the game at all. This is finding the solution. What am I trying to say? If you run the GUI, that tower, if you don't change direction, should hit you square on every single time. It should be able to compute that fast within milliseconds. So if you can get it accurate and fast, then you got a really solid implementation. Like these towers, every time it shoots, that tower is taking my current location and velocity, computing where to shoot using the genetic algorithm, and then firing and still able to hit me. I say that and I changed direction, that's why I missed that one time. We have 3 minutes. I want to start on time. I'll try starting the stream earlier like this, and then I can start on time. Gen Algo, definitely check out these resources I give. One of them's just Wikipedia, but this, I think, explains it in a more digestible way. I don't even attempt to fully explain what a genetic algorithm does in the assignment itself. But go through this tutorial with ads, unfortunately. Go through this tutorial and it'll give you a good idea. The one big difference here is these genes. These are going to be lists of doubles instead of binary values in our implementation. So like for a line, you'll have a list of 2 values and they'll be doubles from any range that you choose. I suggest negative 100 to 100 for the doubles, and then use those directly as your slope and y-intercept. But go through this, and this is going to help you understand what your overall goal is to be able to build, and then worry about the assignment once you understand what you're actually trying to do. Oh, they do give I forgot they do give a real value example in here. But if you don't go through this, the links that I provide there, it's going to be a lot tougher to understand what the hell's going on with this assignment. Grades still have been updated. Oh yeah, I plan to be doing a lot of updating of grades in the near future. Not exactly sure when I'm getting to all of it, but like the homework, the AO2 grades since the interviews, I haven't updated those since the interviews, and all the back grading, all the makeup opportunities that y'all have been doing, I got to update. And then of course after today, LO3 will be the big priority because that's the only non-makeup thing that I have to get out there. So LO3 will be the biggest priority. And then of course after the genetic algorithm deadline, I always want to give the extensions out within 24 hours of the deadline. So those 2 will be taking up a lot of my time. I'm not sure exactly when I'll get to all the makeup grading. Makeup grading is usually deprioritized. Cianatri, what's up? Marcos, please use an ad blocker. I just don't have an ad blocker installed on this machine. And that, which actually I thought I did. No, I don't. Yeah, I don't have it on this. This desktop, I pretty much only use it for streaming lecture. So I don't have all my stuff set up the way I like to have it all. Wish I could have an ML machine so that Gen Algo runs faster. So that server that I just showed, it's a DigitalOcean server, and it's kind of bare bones. I think it's half a gig of RAM and one core, a single threaded, a single core CPU. There's not a lot of power on that server. The Gen Algo should just be efficient. It shouldn't need it should be able to run on your phone just fine. What's up, CSE review sessions? Whoa, nice to have you here. Oop, oop. Yeah, Apple has a built-in Chrome ad blocker, but it wasn't getting those ads. All right, so yeah, big payment time. Well, that's the idea. You write efficient software, you shouldn't need a lot of hardware. Unless you're really doing some big stuff. Like AAA gaming is going to need big hardware because, look at what they're doing. In a 60th of a second, sometimes they're rendering all of that. Like everything that you see, high graphical fidelity. You need big power for that. Unless you're processing large graphics or doing other, really crazy stuff, you shouldn't need a lot of hardware. But anyway, yeah, thanks, Byte. It's start time. Yeah, 1 minute late still. Okay, let's get into this. Binary trees and traversals. Let's talk about it. So hopefully you're all good with linked lists because we're moving on. So the lecture question today, of course, won't make sense unless you've already read the slides ahead of time or watched my video from last semester, which, by the way, since we're in the period where we were remote last semester, all these lectures are posted on YouTube. Actually, I think they are anyway, now that I think about it. We posted all of them last semester. You can go to the same YouTube channel and just scroll down to the older videos. You can see all these videos if you want to get ahead of things. Given how many of you are behind, it probably doesn't apply to very many of you. But unless you looked ahead, this shouldn't make sense to you yet. But after today's lecture, it should make a lot of sense to you. So what an expression tree is, for example, we don't know what that is yet. But take the expressions tree object that I have in the repository, in the examples repository, just like we did on Monday with the linked list node, where you took that class and then expanded it for your submission. You're doing the same thing. Take expression tree and add an evaluate tree method that takes the root of an expression tree and evaluates that expression tree. So an expression tree is going to store an expression like we saw on Wednesday's lecture. It's going to represent an expression. And your goal with this lecture question is to evaluate that expression. With some testing in the expression tree object in the repo, there is some sample usage there. You can use that to get an idea of how to start your testing and kind of transform what's given there as a test case. So there's not too much work to do on the testing side. But I did cleverly make sure that what I gave you there doesn't satisfy all of the incorrect solutions. So you will at least have to write one more test or modify the existing one to get it done. But I gave you a huge start on the testing with that example. Is it not that this is what we have to do? Oh, it's not the actual CSE review sessions. Oh, you tricked me. So let's talk about binary trees, or trees in general. I'm going to stick to binary trees, but you can have, well, let's just get into it and talk about what I mean by that. So these are very similar to linked lists, where with the linked list, each node contained a value and a reference to the next node in the list. A tree is still built on this node structure, but instead of having a reference to the next node, it's going to have two references to two different nodes. And that's the whole difference. That's the whole difference between a linked list and a binary tree. We could just be done with lecture right now and call it a day. But we need to explore the implications of that. So instead of just one reference to the next node, we have two references, which we'll refer to as the left and right reference. And there's a little bit of vocab. I won't belabor the vocab too much here. But when we talk about trees, we like to add a lot of relations to like family trees. So the left and right nodes are going to be the child nodes of that node. So each node is going to have two child nodes. And from the perspective of those child nodes, that node is their parent node. So if a node is referred to by another node, that's its parent node. And if a node refers to another node, that's its child node. Then the vocab can expand to like grandparents and cousins and all that. In the world of trees, people like to borrow all that terminology. So if you see that out in the wild, that's what they're talking about. They're talking about trees and based off of this child-parent relationship. We call these binary trees. What we'll cover today, we'll call binary trees because they have references to two nodes. If they had references to three nodes, they'd be ternary trees. Is that the right terminology? But you could have any number of nodes. You could have a node refer to a list of nodes and have infinitely branching out trees. We're going to keep it simple and keep it to two because anything you can do with a binary tree, you actually can build. You can represent other types of trees, using some reduction stuff that we don't have to get into. But we're going to stick to left and right node just to keep this as simple as possible. Yeah, doubly linked list has two references as well, but it's a bit different. So doubly linked list has that strict structure where if a node refers to another node, that node also has to refer back to it. So if a node has a next of another node, that node has to have that node as its previous. So you do have two references in a doubly linked list, but you can't have any branching out. It still has to be a list structure. Where with trees, we're going to be able to build structures like this, where we have a branching out structure. And to go with the more trees in nature terminology, we have some of that as well. The node that we refer to, we only have a reference to the first node, the starting point of our tree, and that we're going to call the root node, or the root of the tree. That's where we start, and then we travel right and left from each node, follow the references to explore the entire tree. Where a linked list, we had just a reference to the first node in the list, which we called the head of the list. Here we have just a reference to the first node in the tree, which we call the root of the tree. So a little more terminology. And any node that terminates, that doesn't have any children, we call that a leaf. Again, sticking with the tree terminology. We start at the roots and we follow the branches out to the leaves. I won't belabor the terminology, but if I do end up slipping those terms in there, that's what I'm referring to. So this is a tree. We have a reference to the root. That's what we're going to store in our program. And that root has a value. That node has a value and can have left and right references, which can be null, meaning that there is no left child or no right child of that node. So this is a tree with the root 5. Its left child stores the value 2. Its left child has the value -3. Its right child has the value 4. And these two nodes are leaf nodes. They don't refer to anything. They don't have any children. So the tree kind of terminates at those nodes. But like a linked list had, just once I read a node that refers to null, that's the end of the list. Here we have a bit more complex structure, just implied by this fact that we have references to two nodes, is that each time we reach a node that has null for both of its references, that's the end of that branch of the tree. But there can be, as we can see right here, multiple terminating nodes or multiple leaves or multiple nodes with null as left and right. And we don't have to be, this is what we call a balanced tree, where each node either has a left and right child or neither a left nor a right child. That doesn't have to be the case. We can have a tree that looks like this, for example. This is a perfectly valid binary tree where the root only has a left branch, that only has a right branch, and then we reach a leaf, and we can have one of these refer to null, one of them refer to something else. So when we write our code, we always have to check, is left null? If not, do something. Is right null? If not, do something. If it's null, do nothing. So just to point that out, this caused quite a bit of, I didn't have this slide before, and it caused quite a bit of confusion. Students assumed that your trees always had to be balanced, so I want to make sure that's clear right off the bat. And then they had code that said, if left not equal null, check right and left, because you know they're both not null, which is a false assumption. You have to check for null and both of them. Yeah, poor tree. So let's build this tree back. Let's give our tree some branches and leaves again. Now we have a happy tree again, a nice balanced tree. So let's take a look at this in code. Oh, well, actually, let me sit on this slide just for a little bit more. So this is the idea of a tree. That's the whole concept there. That's what a tree is. And just like linked lists, it didn't take us long to introduce what a linked list is. It's built off of nodes that have references to other nodes, and each node has a value. Same thing with tree, but we have two references instead of one. It doesn't seem like that big of a change, but the rest of these two lectures, like 10 minutes to introduce trees, and then the rest of this 40 minutes, and then another 50-minute lecture talking about the implications of this. The implications of having two references instead of one becomes a lot more complex, and there's a lot to talk about. A ridiculous amount. You could have an entire course just on trees. In 250, you're going to talk about trees a lot. In this semester, it's just 2. In 116, it's just 2 lectures. In 250, I don't know how much of it is, the course it is, but it should at least be, I would guess, 2 weeks at the very least. Probably 3, maybe more. There's a lot to talk about. Even though introducing what a tree is, yeah, two references instead of one. Other than that, it's like a linked list. The implications. So hopefully everybody's good on what a I do speak for the trees today at least, and so hopefully everybody's good on what a linked tree, binary tree is. Are there any questions on the definition before we start getting into the implications of what this is, what this means to us as programmers? Are the values going to be hard-coded? Just like the linked list we built, they will be mutable. So you can change the values, but we're not going to do that. We're not going to take advantage of that. So I could, I'll have these as vars. The value is going to be a var, but it very well could be a val. I'm just not going to take advantage of that. But that's less important to the point of just learning how trees work in general. We're not going to get too deep into trees in just 2 lectures. But technically, we will be able to change the values. Both the lowerx and the one slur. I'm conflicted. All right. So let's look at this in code. So that's how it works visually. In the code, we have 3 values that we need to store at each node. The actual value that it stores of type A, so we can have trees of any type. In this example, we'll build a tree of ints. So a value, that's the value that's stored at that node, which would be the values here, 5, 2, -3, 4, whatever we're actually storing in this data structure. And then the references to the left and right children, which can be null. We're going to use null again, just like we did for the linked list. So we have a left child, which is a reference to a node, a binary tree node, with the same type parameter as this node. We have to have the same type throughout the entire tree, and a reference to the right node. So to create this tree, we're going to create a new node in the heap. We'll have a reference to that node. So if I want to create a new binary tree, I'll create a new node with the value 5, and we'll build the tree from the previous slide with the value 5 and no children. So we'll say no children just by saying null and null. And as opposed to linked list, I started at the end of the linked list and built it backwards. Here I am going to start at the root and build this forward for what it's worth. Create that node. Now I have a reference to that node that I just created. And now I can access its left and right variables. I did make these variables so I can change their values. This is mutable. This is a completely mutable tree. The values can change, the references can change, the structure can change. So we do have to be concerned about passing by reference and having a method destroy our tree as we work with these trees. So then I'm going to set the left child to a new node with the value 2 and no children. So I'm replacing this null right here with a new binary node, a binary tree node. I'm going to replace its right child, which is currently null, with another new node. So I'm creating new nodes in heap space. I'm getting references to those nodes, and I'm storing references to those nodes in my root node based on its right and left variables. I'm going to do the same thing for those children. I'm going to finish out this tree, create a new node with the value 3, set that to the root's left child's left child. So going back to our visual, we have this as our tree after those first 3 lines. And I'm saying root dot left equals new node with -3 null null. And then the next line I say root dot left dot right equals new node with a value 4 and null null. So that's exactly what we're doing in these 2 lines. We're saying root dot left equals new node with the value -3 null null. Root dot left dot right equals a new node with the value 4 null null. So we're building that exact tree that we saw on the previous slide. Your methods are chopping my trees as fast as you please. I'm going to have to watch that movie again now. Hopefully that's sinking in. I don't see any questions. Yeah, no leaves during the winter right now, unfortunately. So this is our entire binary tree node class. This is all we're going to do with the node class in this course for binary trees. If you look in the examples repo, this is the entire class. There's nothing else in there. We will write methods that take the root node of a tree, just like your lecture question today. You're taking the root node of a tree as a parameter and then working based off of that. But unlike the linked list where we added a bunch of functionality right in the node class itself, we'll do things a little bit different for a binary tree. So what if I didn't set the to null? So I could actually create this entire tree in a single line. I could say root equals new binary tree node of int 5, new binary tree node of 2, of new binary tree node of -3, comma, new binary node tree of, I lost my place, 4, null on those ones, comma, see, I'm losing track of where I am just doing it. This is why I split it into multiple lines. New binary tree node of 8, comma, new binary tree node of 7, null, comma, new binary tree node of 14, null, and then close on my parentheses. You can actually do that all in one shot. I just broke it up so it's more explicit what I'm doing. The roots left is -3. It just makes it easier to read instead of having one line that, would obviously go off the slide here. All right. So what do we do with these trees? Now that we know the structure, we've seen the code of how to build a tree. What are we going to do? And today we're going to focus on tree traversals until we get to expression trees towards the end. We're going to focus on tree traversals, which is just asking the question, how do we visit every node in a tree? So let's forget about doing anything complicated, anything too complicated with these things yet, and just talk about how do we visit each node in the tree. And for this, we're going to take a first order function that takes an element of the, one of the values in the tree and returns unit, which I'll just give the print line function for our purposes here. And just call that function on every element in the tree. That's all we want to do here. We're not getting too fancy. We're not getting too complex. All I want to do is traverse this thing. With a linked list, we just called .next until we read null. Once .next was null, we said we're at the end of the list. We visited every value. And I did that recursively. I said if next equals null, just call the function on this node, and that's it. Else, call the function on this node, and then recursively call the traverse method on .next. And we got that method called on every node in the list. So here, this is a little bit different because we have two children. So let's talk about the differences. And the code itself isn't going to be that different, you'll see. And we'll talk about this in 3 different approaches. So the order in which we visit the nodes is up in the air. With a linked list, it was easy. Just start at the beginning and go to the end. Done. There's no decision to be made. But when it comes to a tree, do we visit the left child first? Do we visit the right child first? Or do we process the current node first? What do we do in what order? So we're going to see 3 different answers to that, pre, post, and in. And let's just go through them one at a time. So a pre-order traversal means we're going to traverse this tree in this order. We're going to visit the node's value, which visit means call the function that we're given on that node's value. Then make the recursive call on the left child, then make the recursive call on the right child. So to do this, we're going to write our method, which takes the root of the tree and a function that's to be called on every single value of the tree. So you're saying, here's a tree, here's the root, a reference to the root of a tree, and here's a function. Can you call this function on every value in this entire tree? That's the goal of this function. That's where you would use this function. And in my examples, I'll call it on the root of a reference to the root of a tree with the print line function, and just print all the values of the tree. Nothing too interesting. Just keeping it simple for the examples. So my recursive method for this, my base case is kind of hidden. So if the node is not null, implying that my base case is a null node that equals null. So if this is called on null, this is false, this is not executed, and nothing happens. So my base case is a node equal to null, in which case nothing happens. My recursive case is call the function on this node's value. Whatever node you gave me, I'm going to call this function on that value. And then I'm going to recursively call this method on the left child of this node, and then recursively call this function on the right child of this node. Since I'm traversing down the tree, one step down the tree, and we're going to assume that there are what we call no cycles in this tree. So there's at no point where a node refers to a node that's further up the tree. So for example, if this node referred, its right child was set to the root node, that strictly speaking would not be a tree anymore. That is one of the rules of trees. We can't have what we call a cycle where we could just run around in circles in this if right was a reference to the root node. So assuming that doesn't happen, we're always getting closer to the base case by moving to one of the child nodes. We're always getting closer to the base case of a node that equals null. We're eventually going to get to a reference that's null, which does nothing, just returns, ends that stack frame, and then continues on with the method. So is the viewer count down? Everyone's working on Gen Algo? Probably. It's I don't know. But I guess when it's recorded and you already put yourself in a jam by starting so late, yeah, I understand that will happen. It's only 50 minutes of their time. Yeah, exactly. And my estimate for the assignment it's right on the top of the sheet. It's 20 hours. If that 50 minutes is making a difference, I mean, that's really tight timing. You probably have a really stressful life if that's how tight your timing is on everything. When you know you have to spend 20 hours on something, start earlier, spend a few hours a day, manage your time. But, they already ignored that advice. They probably heard it all throughout high school too and ignored it all the way up until you got to me, so whatever. So an example of this, pre-order traversal, if we call this on the root node here, we have a reference to this node, and the print line method, call that on each node. If we do a pre-order traversal, we're going to call the function on this node, which prints it to the screen in this example, makes a recursive call on the left node, prints it to the screen, which makes a recursive call to its left node, which prints it to the screen, makes a recursive call on its left node, which is null, so nothing happens, and we finally start moving up the recursion, makes the recursive call on its right child, does nothing because it's null, goes up the recursion. This is done. It called it on itself and made both the recursive calls, so that stack frame is done. Goes back up here, makes the recursive call on its right side, calls the function on 4, prints it, 2 recursive calls, returns, makes a right subcall, prints 8, makes the left recursive call, prints 7, null, returns, right recursive call, 14 printed to the screen, null, returns, and the recursion is over. I will go, when we get to in-order traversal, I'll go through that a lot slower and with, visuals and everything. But for each of these, I do at least want to quickly go through each one. So the next one we'll talk about is, I get a sense of excitement when I see live Jesse. Hell yeah. Whoop, whoop. And I make your day better. I'm so glad I can help. So the next one is post-order traversal, which is kind of the opposite of that one. We're going to make the two recursive calls first, and then call the function on the value that we're at the node we're currently at. So just a little bit different order. All we do is move the call of f of node.value from the first line to the last line, and we get a completely different order in which we're visiting the nodes. So with a post-order traversal, we're going to make our recursive call call on the left node, recursive call on the left node, recursive call on the left node, null does nothing, recursive call on the right node, null does nothing, and then call the function. So -3 is the first thing that's printed. That returns, recursive call on the right, two null recursive calls, call the function on that node, returns, call the function on that node, return, recursive call for the right, recursive call for the left, recursive call for the left, recursive call for the right, call the function on this node, return, recursive call on the right, recursive call on the left and right, call the function on this node, return, call the function on this value, I should say value instead of node there, print that to the screen, return, call the function on this value, and then return. So we get a completely different order when we traverse in a post-order traversal than we do within pre-order traversal. So the last one, in order traversal, we're just going to put the function call in the last spot that we have available. We're going to put it right in between the two recursive calls instead of before or after both the recursive calls. And this one I want to break it down a bit more. Here are three things. I almost deleted this slide too. I should have either put them in the middle, put the call in the middle of the two recursive calls, before the two recursive calls, or after the two recursive calls for in, pre, and post-order traversals, respectively. So let's break this down and go a lot slower through this example for an in-order traversal. It's been raining here too, Ellipso. The weather's getting dreary. Getting rainy and cold. So let's step through this in-order traversal step by step. So we're going to call this on the root of this node. That's our first call to this method, and then that's going to make many recursive calls. And we're just going to, again, print the values as we visit them. Yeah, and we're hitting, apparently, someone was just talking about, we're hitting daylight savings soon. That it's going to get dark so early. I can't stand it when it gets dark at like 5 p.m. Those days start really sucking. But we got a little more time to enjoy daylight. And so let's go through this. So when we get to the root node, we have this first top level call. And we're calling in order traversal on this node. And we need to go through these lines one at a time. So the first thing we do, the node isn't null, so we're going to call in order traversal on this node's left child. So this frame is still on the stack, waiting on this line, waiting for this method call to resolve so it can continue its execution. So it's going to make this recursive call, and it's just going to sit there idling. It's not the top frame on the stack, so it just has to sit there and wait. There's no way to access the second element on a stack. Based on how we know stack works now after the stack lecture. So we're going to put this frame on the stack. We're going to get this call with this frame. So now we have in order traversal of the root's left node. That's going to make a recursive call to its left node because its node is not null. So we have two frames sitting there just idle on the stack waiting to gain control of the program again. And our execution is now on this node. We have in order traversal of the root's left. So we're sitting right here making this call. This node is going to make that call as well. So all four of these stack frames are sitting on this first line waiting to resolve. This fourth one, actually, node is null now. So it's not going to make any recursive calls. Nothing happens. And it's just going to return. And that stack frame is destroyed without even having to do any work. So now we give execution back to this stack frame. This stack frame gets control of the program again. It's happy. This line resolved. So it gets to move on to the next one. Call f of node.value and print -3 to the screen. Its next job is to call in-order traversal on its right node. That node is null, so nothing happens. That stack frame returns. This stack frame reaches the end of its execution. This stack frame returns, and execution goes back to this node containing the value 3. So now this line is done with this in this stack frame. So in this stack frame, execution moves on to the function call, and we print 2 to the screen. The next thing this stack frame needs to do is call in-order traversal on the right node, make this recursive call on the right side. This recursive call, this stack frame, is going to call in-order traversal on its left node. That's null, so nothing happens. Make the call f the function on this node's value, which prints 4 to the screen. Then make the recursive call on its right node. That's null, nothing happens. This stack frame is done. Hits closing braces, returns, destroys that stack frame, pops it off the program stack, gives control back to this stack frame, which is working with, on this stack frame, the node input is this node. That stack frame is done. We're hitting closing braces, so we return execution back to the first recursive call. We only have one frame on the stack at this point. We're back down to the top level call on the root node. That call, this is the call that just returned. It's in-order traversal of node.left. That call just returned. So execution returns on this line. We call f of this node, print 5 to the screen, and then make the in-order traversal call, the recursive call on the right node, and move execution down here. And on the right side, I'll skip some steps. I won't go through all the steps again. But we make the recursive call on the right node, which makes the recursive call on the left node, which makes the recursive call on the left node, prints out 7 to the screen, makes the recursive call on the right node, and then returns execution back to this stack frame. We go back to this stack frame, print 8 to the screen, then make the recursive call on the right node. That makes makes a recursive call, prints 14 to the screen, makes another recursive call, and then returns. This stack frame is done. That stack frame is done. This stack frame is done. We hit a whole bunch of closing braces. All the stack frames start returning. Well, not returning anything because it's return type unit, but they all start getting popped off the stack, and we get back to whatever method called in-order traversal in the first place, and we give control back to that method. Is there any difference between the three approaches performance-wise? No. I mean, maybe if you have a really specific structured tree, maybe there's a tiny difference. Asymptotically in Big O notation, there's no difference performance-wise. It depends on what you need. It's going to determine which traversal you use. Which of these traversals does it the fastest? Yeah, I don't think there's any performance difference, though. Nothing significant. Challenge, write with loops. That's a good challenge. I agree with you. So my challenge to you is to write these with loops. I'm curious if you looked ahead on the slides and knew that that was coming, because that's definitely the point I want to make here. Stop giving them ideas. I actually, off screen, I edited and added this slide right when I read that comment. No, you looked ahead. All right. So my challenge to you, for all of those non-believers in recursion, write any one of these methods without recursion. Now, this isn't a requirement. Maybe sometime I should require this. But if you don't believe in recursion, definitely try this out. If you ever come to me and say, I don't understand why we learn recursion, I think it's dumb, or whatever, you say that to me in office hours or something, I'm going to say, oh, that means you wrote one of these tree traversals using a loop. Can I see your solution? And then they're going to say, well, I didn't do that because it wasn't for a grade, so why would I do something optional? And then I'll say, because it'll get rid of your stupid opinion on recursion. Recursion is powerful. Up until this point, any way that we used recursion in this course there's a strong argument to be made of why are we using recursion? Why did we even do this? At this point, you should see how beneficial recursion is, because these methods, very trivial to write using recursion. This is as concise, basically as concise as you can get code that does so much work. Try to write these without recursion, and you'll see why we use recursion, because this is why it makes things so much simpler in specific applications, specifically for trees and graphs that we'll talk about next. I don't think I have a recursive example in graphs, but depth first search would be the recursive example in graphs, which unfortunately I just can't fit in the course. But write one of these. If you don't believe in recursion, this is my challenge to you. If you don't believe in recursion and if you don't accept this challenge, you're gonna have to believe in recursion on blind faith, because these would be very challenging. It's certainly possible. Obviously, you can write them, but it's a lot more work. Or try to do today's lecture question without recursion. Those of you who aren't comfortable using recursion when I'm not forcing it, like I don't ban var for this lecture question. So if you try to do this lecture question without recursion, you're going to be writing a lot more code and doing a lot more work than you would if you don't use recursion. So if you're not a believer in recursion, maybe this just happens naturally. Maybe you just will try to not use recursion for today's lecture question, and I don't know, either you'll get super discouraged, or at some point you'll be like, well, maybe I'll try that recursion thing the professor was ranting on about. And then you'll use recursion and your whole life will get better. Recursion will, I don't like making too bold of statements, but recursion will improve your quality of life. Recursion is the best thing ever. I don't know. I don't want to stop that, but recursion's awesome in certain cases. Trees is one of them. Doing anything with trees without recursion, it's really the reason. It's been contemplated before. Like, do students in 116 need recursion? And we keep coming back to, well, if we're talking about trees, we better be talking about recursion, because making them work with trees with loops is torture. We can't do that to them. Yeah, I'm a big fan of recursion. It's another tool in your toolbox. Like, I don't look for reasons to use recursion, but there are certain problems that just ask for recursion, beg for recursion. Finding all of the like the anagrams, not the anagrams too, kind of, but like what's the example I'm trying to think of? Finding all of the, so given a set of characters and a length, like say given all the lowercase, uppercase numbers and special characters, and length 8. Like, how many passwords can you possibly make with all those characters? And that's an example that I give in 199 as well. And I use recursion, but I don't expect them to understand the recursion and that. But that's one natural case where it's like, I just want to use recursion for this because it makes my life easier. So let's talk about an application of trees. We talked about trees and tree traversals, but it's all with no context. We just learn trees for the sake of learning trees. Let's see an application of that where, did I say 191? I meant 199 if I said 191. I meant 199. 191, I think you do a lot of recursion, don't you? I think that's a way of life in that course, if I'm not mistaken. Maybe I'm mistaken. So let's talk about an application of trees. Why should I care about trees? Well, here's one application. I might not sell this completely to you, why you should care about trees, but at least give you a way that you can use trees, and that's expression trees. So last time we saw an expression, we saw an infix version of the expression and a postfix version of the expression. Let's talk about another way to represent expressions, and that's going to be through expression trees. So we're going to use a tree structure to build our expression, where each node in the tree, each node's value can either be an operator or an operand. If it's an operator, we're going to evaluate that operator on the left and right child. If it's an operand, we're just going to use that as a strict value in a number in this case. And the operators, the left or right child are the operands, and the operands can be other operators. So what does that all mean? Well, let me just show you. This expression that we saw, except I don't have the times 2 at the end here. This expression represented as an expression tree would look like this. The root node is the operator that is evaluated last. I don't know if I want to sell it like that though. But this means we're going to take the subtraction of the left and right nodes. The left node is itself subtraction, which is the subtraction of 12 minus 4. So we have 12 minus 4 minus the right subtree, which we put the parentheses to denote that, 8 plus the division of 9 and 3. And we can represent this entire thing as an expression tree. So if we have an expression tree and we need to evaluate it, conveniently exactly what I'm asking you to do today, in your code, this is what you need to evaluate, is find an operator with 2 operands as leaves that are not other operators, and evaluate them. So 12 minus 4, we have 8. We find another operator with 2 numbers as its operands. So that's one that we can evaluate. We know we can evaluate this division because there's no operator as one of its things. We can't evaluate this addition yet because it has this division which needs to be evaluated first, which is kind of how your order of operations is represented in these trees. So, and then we just keep going up the tree. We have this addition, 8 plus 3, 8 minus 11. And once we have one value, then that's when we're going to get a resolution. I was trying to figure out if that was an insult or not. Have your mom do it. You're talking about cutting hair. I think that one's okay. I'm like, was that just your mom joke in my chat? All right, but anyway, we got down to a single value, so that's the evaluation of that expression tree. So if we have a tree, got him. If we have a tree that's representing this expression, like we did on the previous slide, we can build that with our binary tree nodes by keeping track of what operators are available. For the lecture question, it's multiplication, division, addition, subtraction. And we're going to represent those as strings. And then for the lecture question, the numbers, the operands, are also going to be represented as strings. And we're going to assume that they're all well-formed doubles. And then in your testing, you should have well-formed doubles as well, and proper structure and everything. So you don't have to do all kinds of checks to see if the expression is valid or not. So with this, if we modify our in-order traversal just a little bit, where we're going to say, instead of just printing each node to the screen, we're going to check if it's an operator. If it's one of these operators, we're going to print parentheses around it. We're going to print parentheses around the whole expression, which is the recursive call on the left and right, with an in-order call to the function, which in this case is going to print to the screen. If we do an in-order traversal on an expression tree, and we add in our parentheses to make sure the order of operations is preserved, we're going to have a fully parenthesized infix expression. So some of these parentheses will be redundant, but it will be accurate. If you look at the innermost parentheses, that's what's evaluated first, either the 12 minus 4 or the 9 over 3, and then the 8 plus 3, and then the overall, whatever it was, I forget, 8 minus 11 for this. So if we do an in-order traversal with just a little bit of modification to get the parentheses in there, we can get the infix expression with full parentheses, fully parenthesized. If we want the postfix expression, we just run our standard post-order traversal. There's no parentheses to add, so nothing to modify. We just give it the function that doesn't print line, not just the print line, but prints whatever we're looking at, and then a space after just to get everything separated. If we call that on our expression tree, we get exactly the postfix expression. And for what it's worth, there are prefix expressions too. I don't think they're really used as much as postfix, but that exists too. You just call it pre-order traversal with print line token space. 250 is way harder than 191. If that's the question. It doesn't matter who's teaching it. 250, there's a lot of really technical content that needs to get covered. 191, yeah, but not so much. Being a 100 level instead of a 200 level course, you should expect that too. So if we did the post order traversal, we're going to get the postfix notation. So recursive call, print, return, recursive call, print, return, print, return, and so on. Print, 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 print. That's how we're going to get the order for postfix. So these are very related topics. Which brings us back to the lecture question. Holy crap, when I start on time, I finish 3 minutes early. You love to see it. So let me talk about the lecture question a bit. So this is going to be a tree of strings. This will be called on a binary tree node of type string. So the operators are going to be just these exact symbols, only these 4. You won't see any other operators, and in your testing, don't add any other operators. And the operands are also strings. So if I had like 3.3, the string 3.3 is a node, I can call 2double on that, convert it to my double, and we're going to assume that they're all well-formed and that the expression tree is a valid expression tree. So what you can do in your code is time for the I won't solve this one live right now, but you can check, is this node's value equal to star slash plus minus? If it is, you know you got yourself an operator, and you got to handle that as an operator. If it's not one of those 4, you can slap an else on that thing and say, else I have myself an operand, and since we're assuming all the values are well-formed doubles, we're just going to call .2double. Either it's multiplication, division, addition, subtraction, or I'm calling 2double on it and treating it as a number. So don't overthink how you're going to tell if this is an operand or operator. If it's not exactly equal to one of these 4 strings, it's an operand, and you can call 2double on it safely. And in your testing, make sure you respect that as well. Don't give like for a node representing 3, don't give it three. That's not a valid input for our testing here. I don't want to have to add that to the lecture question. Like, make sure you validate all the inputs. Make sure you validate that this is a valid expression tree. I don't want to have to add all those requirements on there. Maybe someday, but you know what? I think you've been through enough this semester. We're not adding that. We're not adding that to it. So let's just assume that they're all valid, and in your testing, make sure they're all valid trees. So that'll be officially the end of the lecture. And let's do some chatting. Yeah, this should come before calculator. Maybe. That's tough, though. I'll tell you the reason why I don't. Is, let's go all the way back. Is calculator is part of the, excuse me. First of all, I could do this, but it's part of the OOP module. And we do have to create a class and then create objects of that type. And we also need some functional programming stuff. We need type parameters. We need first order functions. There's just a lot of stuff that we need that I take advantage of the fact that you already know these things as we talk about this stuff. So it could be done, but it would take quite a bit of restructuring of the course. But I have thought about that. I even actually had an expression tree assignment in this course, where you had an expression tree which wasn't restricted to just these 4 operators and wasn't just restricted to doubles, and you had to have a fully generic it wasn't expression trees. It was expressions without the trees, where you just got a string which represented an expression in infix notation, and you had to evaluate it without knowing anything about it. It had to be completely generic. And then the 2 examples that I gave were arithmetic like this, where you were given the operators and the order of operation, And then we could also use your same exact code to do binary expressions. So if you had Boolean values ANDed and ORed and XORed with each other with the appropriate order of operations, that your solution should be able to handle that without even knowing what it's doing, just by getting the order of operations and the operators as parameters, and then being completely generic in resolving any expression that you were given. I haven't ran that assignment in a bit. It's a fun one, but it was really related to calculator, and I was always trying to get those two to be right next to each other. It would take too much reorganizing of the course. But that is something that I've thought about, is doing this closer to calculator. Of course, if I did, knowing me, I would add order of operations to your calculator assignment and just make calculator way too hard. So it's probably better off that we don't do that. There are a few assignments. I'm actually for LO5 for AO5. I mean, this semester, there's an assignment that I want to make. I should have at least one new one each semester. I want to get a new one out this semester. But I got some ideas for longer term too. That I don't know. We'll see how it all pans out. See how much time I get to work on them. Yeah, calculator. I've thought about this before. I don't think it's possible, but doing calculator with no control flow, but also handling order of operations, I don't think it's possible. Some of my TAs have tried in past semesters, tried to convince me that's possible, but they were unsuccessful. I don't believe it's possible. I'm pretty sure I could write a proof to prove that it's not possible. Gen Algo should be buffed to be a full-on neural network. I mean, it kind of is. The expansion objective of genetic algorithm is literally using a genetic algorithm to train a neural network. I could just make that part of the assignment instead of optional. And then the other, maybe more of what you're suggesting, is to have that assignment create a neural network and use things like backpropagation to train the neural network without using the genetic algorithm. Because genetic algorithm is very inefficient, by the way. There's a reason why, like, you won't see genetic algorithm in a legit like AI or machine learning course. It's because it's very inefficient. It's effectively a glorified guess and check algorithm. You create a bunch of random genes, you throw them in the cost function, see which one does best, and then you go from there. But you're just guessing, checking, and doing that over and over and over again until you start converging on to an optimal solution. It's not efficient. So yeah, if you're actually taking a machine learning course, there's a lot more work to do, a lot more math to do. But that's exactly what makes Gen Algo possible in a 116 course. Like, I can't really make you do much beyond that. But I did want to get some form of AI in this course. That was my goal. But something that wouldn't absolutely crush your souls. Even Gen Algo, it's claimed some souls. So it might not be the best thing to hear that, trust me, this is as easy as AI gets, but that's as easy as AI gets. Yeah, raid the day one straight. Next semester, you mean? It's I think it's at the same time next semester. I forget. I looked at the schedule, but I think it is at the same time. Or no, maybe it's a little later. It's not important right now. I think the schedule is out, right? I think y'all can check, right? I am talking about hey, maybe this is a good chance to get feedback from all of you. Let me catch up on chat first. But I want to restructure the course a little bit next to... Oh, come on. I would have to remove microwave. With genetic algorithm, I had that problem with genetic algorithm last semester. I had this recommendations homework, which took the purchases... data of purchases of various customers of various items, and if somebody's purchasing, based on that data, if somebody's purchasing one item, what would you recommend to them? What should go in that? Hey, you should also, people who bought this also buy, and running all the math with that, with no variables. Problem was, most of the class did that one because it was easier. So I removed it, and that's what I would have to do with microwave as well. All my homies hate microwaves. I like the microwave assignment. I don't know. Maybe it's just me. Maybe it's because I wrote it that I like it so much. I had fun making that one too. I was just playing. I found out my microwave does things I never knew it did just by playing with all the buttons and just seeing how my microwave behaves. So I modeled that assignment after my microwave. So hopefully it's realistic. Hopefully that's typical of most microwaves, how mine works. Like, for example, when you hit the popcorn button, if you're like in the middle of adjusting the power level and you hit the popcorn button, like what's supposed to happen, I decided based on what my microwave does. So whatever that assignment says, that's what my microwave did when I tested it. Like if you open the door, hit popcorn, close the door, and hit go, like that's what my microwave does. That's what made it into the spec. I might have to get rid of rhyming dictionary or beef it up. I beefed it up this semester. Believe it or not, that was even easier before. I didn't have... the primary objective last semester was finding all the rhymes, and that's it. I added rhyme length, and I added best rhyme this semester to give it a little more meat, and it's still easier than Physics Engine. I might get rid of rhyming dictionary entirely because there's just so much good content to Physics Engine. I firmly believe that students learn a lot more doing Physics Engine than doing rhyming dictionary. And the students who do Physics Engine do better later on in the course, but I don't know if that's because they learned material through Physics Engine or they're just, you're the students, those of you who did Physics Engine, the ones who just aren't afraid of a challenge and you want to take on more. So I don't know if it's just a correlation, not a causation, but I do want to get rid of rhyming dictionary and test that out to see if students will learn more by giving them a harder homework 1. That should make homeworks 2 through 5 easier, because they'll learn more. But there's a lot. I even have lecture examples where I talk about Physics Engine. If you did rhyming dictionary, it's really hard to follow those examples. Like when I'm dissecting jumper and the jump mechanics and stuff like that. If you did rhyming dictionary, you might not know what I'm talking about. Even though I say, if you did rhyming dictionary, read the Physics Engine doc at least to get ready for this. I know nobody did that. Like nobody's gonna do that. I'm gonna have to force them to. So I might remove rhyming dictionary. Building MMO from scratch. I tried that the first semester. You might be surprised, but it didn't go over that well. It didn't go over terribly, but it's a lot. Like, there's a lot to do in that. And if there's anything that you miss throughout the course, you can't do it. You can't really do it. I don't know. I might do something with that, though. But as it stands now, I give you a lot of the MMO code. That's actually AO4 is the maze solver thing. So I give you most of the MMO code, and all you have to do is the pathfinding part of it. So that changed quite a bit. But yeah, the first semester I had them writing towers. Towers was a 2-part assignment that when I go to jessehartloff.com, and they, across 2 assignments, they built a large portion of that game as their assignment. And then I posted my solutions, and I hosted that so they could play the game and see what they were building towards. It was a lot, though. You're not going to be surprised to hear that a lot of students didn't do so well. Rhyming dictionary is too... It's not just too easy, but it doesn't test the things that I need to be tested. So by the time you're done with homework 1, I need you to have a good understanding of objects, classes, and pass by reference. And rhyming dictionary doesn't really hit those points as hard as I need it to. Where with Physics Engine, updating the previous location, you got to be thinking about your references. If you don't think about your references, you get in trouble with that one. And just passing objects and changing their state across function calls and having method calls with side effects and things like that. Rhyming dictionary just doesn't have any of that. You create a map to store your dictionary words, and like that's it. That's all you do is in terms of classes and objects. There just needs to be not even necessarily more stuff, but it needs to be testing the right concepts, and it's not doing that right now. So that needs to be changed. Yeah, you should be able to solve rhyming dictionary in like 10 minutes right now. And I always recommend that. Like, go back to a 115 assignment that really kicked your ass and do it right now. Or, a homework 1 in this class. And just get that realization of how far you've come. Like, you might always be struggling. You might always feel like you're not learning, or that you're not, everything's a challenge. But that's because the courses are designed to always challenge you. We're always pushing you to the next thing. If you go back, even a few weeks in content, you should be able to see how far you've come. And if you're keeping up with this course, you are learning a lot. You know a lot of stuff right now about computer science and programming. OOP and FP and stack and heap memory, data structures, how linked lists are created. You've learned a lot of stuff. And if you're surviving at all, you are doing great. You are doing fantastic. Even if you're behind on lecture questions by, a week or two, you're still doing fantastic. So if you need a confidence boost, go back to an older assignment that you struggled with in the past and just knock it out of the park. And if you don't, go back a little further. Go back to a 115 assignment. Fire up UB Infinite and go to one of those pre-labs that kicked your ass and see how fast you can kick that question right back. Oh yeah, this was the problem. This is why I added why I added rhyming dictionary. I had some students who never took physics and they were just really lost with Physics Engine. So if I get rid of rhyming dictionary, I might have to have lecture content on the physics specific aspects of that assignment. But if I only have one assignment, I can also dedicate lecture time to it. So I can't really dedicate lecture time unless there's only one assignment for that learning objective. Because if I just pick one and talk about one of them, like I kind of do already with Physics Engine, I'm missing the parts of the class that didn't do that assignment. Like that expansion. I forget what I was talking about 10 minutes ago. The expansion. If you mean the neural network, I mean that's the expansion now. If you mean the neural network with back propagation, yeah, maybe I'll add that as another one. Yeah, exactly. Trial and error, guess and check. There's nothing fancy. There's nothing sophisticated about genetic algorithm. It's glorified guess and check. The next big thing after GA is maze solver. You're gonna write. I'll have the GUI where you have a character in a maze, and you click anywhere on that maze, and the character should take the shortest path to get to that destination. And I'll have the whole GUI. It'll be I believe I have it set up as a web app. So you'll run a server, open it up in your browser, and then click around, and you should see your character move following the shortest path. I still have to update this. That's one of the things I'm behind on. It's been a week now since the last interview. I got to get on that. I'll get that done for you. Right. Yeah. I haven't processed the interviews yet. The TAs had done everything on their end. They've been done for a while. It's just me. That's my bad. I gotta update everything. And the only reason it takes a bit of time is I want to do my verification. I just want to make sure everything's legit, or else I could just post what they came up with. But I do want to do a once over and a few spot checks and make sure everything's on the up and up. And sometimes, especially with the homeworks, there are some times where I make decisions like, you know what, that's not that bad. Let's give that student credit. So I want to make sure none of those get through where I think they deserve credit, but they technically didn't get credit. I want to make sure they get credit. Especially when it comes to decisions that my TA shouldn't be making on their own accord, like waiving the auto grade requirement. That's something I want to do. Repeated this course 5 times. I keep just guessing. Maybe on the 100th time, my gen algo will start to converge. Page down. I should just skip a few. Most famous microwave UP. My homies hate rhyming. And if I do ramp up rhyming dictionary, I would like it to be useful. Like if you're trying to put together lyrics for rap or a poem, I'd like it to be actually useful for that purpose. But that would take a lot of time to get the assignment just right. I'd have to change the definition of a rhyme from what it is now, and um, I don't know. It would take a lot. Might be worth it, but there's a possibility that it wouldn't be. So it's hard to sink that much time into it. Remove microwave and rhyming dictionary. Microwave's not a problem since people think calculator is easier anyway. Microwave's not an issue. I think microwave's a little bit easier personally. I'll stick by that, but um, students don't agree by the majority. Yeah, rhyming dictionary is too easy. I gotta get rid of it. Yeah, exactly. Yeah, I do this sometimes. If you've clearly been working really hard and you understand all the concepts, sometimes I end up doing that. I'm just like, you this tiny mistake that has nothing to do with your understanding of what's going on, you know, that just fix that. Sometimes I do that. As long as you understand the concepts, as long as that's clear to me. Is operator table defined in the main method? I think it's just the way I set it up. So the expression tree class or object in the examples repo, there's some relics from the expressions homework back when I used to have that homework assignment. So like that table, and there was that, and then an order of operations. Yeah, the table, which is a map from string to function. I was doing that to show them what the protocol was for the homework assignment, but it's not really relevant anymore, especially not for this lecture question. You can just assume it. You can just hard code to addition, subtraction, multiplication, division this semester. Oh man, I only left a minute left. Yeah, y'all are doing awesome. Those of you who are still not completely throwing in the towel and giving up on the course, you're doing great. I'll reiterate that because this course can even I see even really good students can feel discouraged in this class, and you shouldn't. If you're surviving this class, you're doing fantastic. You can move. Yeah, you can just and I mentioned this last time. It's worth repeating. Anything in the examples repo is fair game to use in your submissions. Since I give you that code, since I was the source and I gave it to you as part of the educational experience, feel free to use it wherever you want. And I make sure that the code that I give, when I write the questions, I take that as an assumption. Like I know you have all this code and access to it, and then the question is on top of that. 442. Yeah, I didn't get to talk about restructuring 116, but I'll give I don't know. Maybe I'll talk about it later, but I want to cut it down to 4 learning objectives. I want to cut down event-based architectures by a lot, roll that into functional programming, have 4 learning objectives, and give them each 3 weeks instead of 2. I think 2 just makes the course a bit too rushed. So that's what I'm looking at for next semester. Trying to give the topics time to breathe. I feel like everything is just so rushed. And then getting rid of like that break week in this MMO architecture. I think I'll either just cut it completely or just find a lecture here and there where I can talk about the topics in those sections. I think that's what it needs when you have more time to like think through the homework assignments, especially.